Symmetry plays a crucial role in physics. Even though the world around us looks quite asymmetric, the universe on a sufficiently large scale is highly symmetric. The uneven small-scale chaos is smoothed out, essentially allowing us to make conclusions about the entire universe even though we are part of a tiny speck of it. And we don't normally think of it that way, but the only reason we could make so much about the entire history of the universe is because the universe is so damn symmetric, which then allows us to test theories and also develop new ones. Interestingly, the universe is very much symmetric, both in terms of stuff being in it, but also in the way that stuff is then governed. As of now, we believe that the way the universe works is consistent across space and time. More formally, the laws of physics seem to work the same whether we are here or some other galaxy far, far away, whether it's now or some billions of years in the past. Now, we can't absolutely be sure of it because, well, lack of evidence isn't evidence of absence. But even if the laws of physics are dynamic with space and time, they change slowly enough that we haven't as yet measured any significant discrepancies. Which is wonderful because just imagine the chaos if the rules of the game changed based on where and when you ask. Which leads us to this insanely beautiful notion of symmetry and how deeply it is connected with the way the universe seems to work. Emmy Noether's theorem. Essentially, it is about a connection between symmetries and conservation laws. What she found was that for every continuous symmetry in the universe, there is a corresponding conservation law. Symmetry in position, the fact that no particular location is in any way special, leads to the conservation of momentum. Symmetry in orientation leads to angular momentum conservation. Symmetry in time, that physics stays the same with time, leads to conservation of energy. The true power of Noether's theorem only becomes apparent when you study Lagrangian mechanics and the principle of least action, where it's like the most relevant. And you could see exactly how symmetries imply the conservation of particular quantities. But all of these things is not just about classical stuff. Even the most deeper theories of reality benefit from the presence of symmetries. The entirety of particle physics, the Standard Model, is based on these theories called gauge theories, which are essentially theories that have a particular kind of symmetry. Gauge symmetry. For instance, quarks, the fundamental particles that make up protons and neutrons, come in 3 different colors: red, blue, and green. Not literally colors, they're not really colors, they're just labels to distinguish between. It's like the positive and negative charge, but for the strong force, and instead of 2, there's 3 of them. Now here's the important part. Intrinsically, there's no difference between what we call the red quark or the green quark or the blue one, similar to how there's no difference between what we call the positive or negative charge. There's the symmetry that exists between the 3 color charges. Only the relative change matters. And that gives rise to what's called, and yet don't worry too much about it, SU3 symmetry, enforcing that color charge must be conserved. This is essentially what quantum chromodynamics is about, the interaction of particles with color charge and the 8 different gluons, the strong nuclear force. Other interactions also have certain symmetries and corresponding conservation laws. The point is, symmetries have been guiding the development of physics. Interestingly, the universe on the largest of scales is symmetric across space. It is homogeneous and isotropic, which is to say there's no preferred direction. However, it is not quite symmetric with time. Things in the far past were quite different, significantly different than today. It was hot and dense, and now it's like comfy and diluted. The only reason we could tell or have a notion of time is because of this asymmetry. If the universe would have been symmetric across time, we wouldn't really have any relevant notion of past, present, or future. Time would exist, but not in the way we know it today. It would probably be just like things happening and changing but not leading to anything. So, yeah, weird stuff. What caused this asymmetry of time? The original low entropy beginning of the universe. When you start from a low entropy state, it's just much more probable that things will get more disordered, giving time an apparent direction. With time, things get disordered. The second law of thermodynamics. The question to ask is, why did the universe start off in such a low entropy state? And which is probably one of the biggest questions in physics, unsolved. Previously, I said that the symmetry in time leads to conservation of energy. But clearly the universe is not symmetric in time. Because of the evolving, expanding universe, the outcome of an experiment does depend on when in the history of the universe was that done. And so fundamentally, energy is not conserved. It is only conserved approximately when the time scales involved are like small enough and the universe expansion can be ignored. If it was new to you, consider light traveling in an expanding universe. We observe the light to get redshifted. Now, redshifted light has less energy than the original. Where did that energy go? Well, in an expanding universe, energy doesn't have to be conserved. It was simply lost. Okay, so far we've talked about things that are symmetric and then things that are not. But sometimes what happens is that things start off symmetric, but with the changes in conditions, they become asymmetric, leading to changes in physics in some sense. What I'm talking about is symmetry breaking. And this is kind of a very usual phenomenon. When water freezes to ice, it loses a lot of its symmetry, which may seem counterintuitive at first considering the crystalline structure of ice looks pretty symmetric to us. But overall, water is much more symmetric than ice because it has a lot more freedom in terms of movement and rotation. Consider this. A lattice structure is only symmetric under certain discrete sets of rotation, while liquid water, because it is not constrained by a lattice, is actually symmetric on a rather more continuous scales of rotation. When water cools, at first nothing much happens, but at a particular threshold temperature, a phase transition occurs and you get ice. A structure we just concluded is less symmetric than what we started with. Similarly, the early universe went through potentially multiple such phase transition events at which we saw symmetry breaking to occur. It is believed that very early in the universe, all the forces were essentially the same, a highly symmetric condition. However, as the universe cooled, multiple symmetry breaking events occurred and all different forces took their different shapes and forms. In the current universe, the mass that we have can be traced to the interaction of particles with the Higgs field, which has a non-zero positive value. But it was probably not always the case. In the very early universe, the conditions were much more harsher and the temperatures were much more higher. So all the fields were fluctuating rapidly, but with a mean value of 0. So all the particles were essentially massless. However, as the universe evolved and cooled, a phase transition occurred, leading to a kind of symmetry breaking. And so Higgs field ended up having a positive non-zero value, a positive energy state. So all the particles that could interact with the Higgs field ended up gaining mass, while those that don't interact with the Higgs field remained massless. The particles that mediate the weak force, the W and C bosons, gained mass after the symmetry breaking event, differentiating themselves from the previous electroweak force, making electromagnetic and the weak forces to be two distinct phenomena of the current world. What we haven't talked so far about are the fundamental discrete symmetries of the universe. For instance, a square has discrete symmetry. It is only a rotation of 90 degrees that leave it unchanged, while a circle can be said to have a continuous symmetry under rotation. You can rotate it by any amount and looks the same. Now, unlike continuous symmetries, discrete symmetries do not lead to conservation loss. However, they are important in their own way because they tell us about the feasibility of certain particle interactions based on whether or not they are symmetric under certain transformations. There are three fundamental discrete symmetries in particle physics. Those are parity, which is to say mirror symmetry. There's also charge conjugation, which say if you flip the charges of all the things in a process, does the process look the same? There's also time reversal symmetry, which is to say does the process look the same forwards and backwards in time? Now, it was thought that the universe obeys all these symmetries individually. And even though the strong force and the electromagnetic force does obey these symmetries, the weak force does not. The mirror version of our universe would be different because the weak force plays out differently in the mirror world compared to the real world. It violates parity, so it allows us to have a way of deciphering whether we are in the mirror version of our universe. It also violates charge conjugation, which is to say it treats matter and antimatter differently. And the fact that we see ourselves living in a world dominated by matter and not antimatter could probably be the result of the weak force violating charge conjugation, creating this matter-antimatter asymmetry that we see in our universe. Now, even though the weak force does violate these symmetries individually, a combined version of these symmetries, the CP-T symmetry, has never been shown to be violated in any system. And for good, because if violated, the foundations of all of physics would start to shake, because so many of our modern theories depend upon these symmetries, because symmetry is at the heart of physics as it stands today. Thanks for watching.